In the last several units, we focused on understanding the structures of monosaccharides. That is the simplest unit of sugars. Now in this video, we're going to focus on disaccharides, molecules where two of the simple monosaccharide units have linked together. There are a variety of common disaccharides, including sucrose, which is most commonly known as table sugar, lactose, milk sugar, of which people that are lactose intolerant are unable to properly metabolize, and maltose, also known as malt sugar. By the end of this video, we will understand the structures of these three common disaccharides, including how we link together monosaccharides to form those, how we classify these disaccharides, and how these disaccharides are metabolized, or in cases of people who are deficient in the ability to metabolize those, why that is the case that they are deficient in the ability to metabolize those disaccharides and what the implications of that are. Now, before we begin to look at disaccharides, what I want to first do is a short review of how open chain monosaccharides, such as the fructose molecule shown here, D-fructose to be specific, undergoes an intramolecular reaction to form the ring that has a hemiacetyl group. It's important to understand this reaction because when disaccharides form, generally they're forming by linking two of these cyclic monosaccharides together. And we need to remember how to recognize specific features of the monosaccharide cyclic form in order to understand how those cyclic monosaccharides are going to link together to form disaccharides. In the case of D-fructose and other monosaccharides, what happens generally is that our hydroxy group here at our final chiral carbon, where we're numbering from the beginning of the chain at the top in this Fisher projection all the way down to give this as what we would call a ketohexose, because as a ketone group and it has 6 carbons making it a hexose. What happens is this very last chiral carbon here, that's at position number 5 of our chain, uses its lone pair of electrons to come up and attack the carbonyl group. In this case, we are dealing with a ketose, so the carbonyl group is at position 2 in this particular case, and that's where we are going to attack. This attack yields the formation of a ring because these 4 carbon atoms here are all still attached to one another. And this carbon at position 5 is still attached to the oxygen. The oxygen circles around and attaches to position number 2 here at the carbon. So that makes a continuous ring system composed of carbons 2 through 5, the oxygen then coming back around to position 2. We need to dissect where each of those positions are in this product molecule so that we can later go about looking in more detail at disaccharides and where the specific linkages are between monosaccharides to yield disaccharides. Numbering our disaccharide here, we look for the hemiacetyl group as our frame of reference because the carbonyl group of our monosaccharide is what will become the hemiacetyl group in the product molecule. We also refer to that as the anomeric carbon. It is the carbon that we classified as alpha or beta when we were looking at the configuration of these molecules. Now, looking for the hemiacetyl carbon in our product, we look for the position where we have a single carbon atom that is part of both an alcohol group here and also part of an ether group coming over, going this way around the ring. So therefore, we can recognize that this carbon is what we'd refer to as our anomeric carbon. We could describe this as a beta anomeric carbon or a beta sugar because of the fact that the hydroxy group is oriented upward at this position. Now, in order to number this molecule, we recognize that that anomeric carbon derived from the carbonyl group. The carbonyl group was at position number 2 of our open chain, so it's still position number 2 here. And then from there we can infer what the other carbons are numbered around this ring. So with that one being number 2, number 1 was a CH2OH group that's connected, so that has to be coming to right here. So I'm going to put that in as number 1. Coming around the ring here would be 3, 4, 5, And 6, and position 6 should be a CH2OH group, and it is indeed a CH2OH group down here in the open chain form. So now we have all 6 carbon atoms of our monosaccharide numbered. This information will be important because a key way that we classify how monosaccharides are linked together to form disaccharides is based on what carbon number of the ring is engaged in the reaction to form the disaccharide molecule. There are a variety of common disaccharides. The 3 that we are going to focus on for purposes of this discussion are arguably the 3 most common, and certainly 3 that are very important for human metabolism and health. Sucrose, the structure shown here, lactose, the structure shown here, and maltose, the structure shown here. Sucrose is commonly known as table sugar. This is the sugar that if you buy standard sugar at the store to make a cake with or something like that, that is that granular white sugar. And in the case of sucrose, if we were to take a look at our chart of monosaccharides and compare it to the structure of sucrose, we would see that sucrose is comprised of a glucose unit, which I will abbreviate as GLU, and specifically it would be a D-glucose unit, because in our Haworth projection, we see that the CH2OH group of the glucose is oriented upward above the carbon. That indicates that the configuration is D. Also, D is the standard configuration that's most common, so it's no surprise that that's the case here. And the other unit of sucrose, the other monosaccharide that makes up sucrose, is a molecule called fructose, and specifically this is D-fructose. We looked at how D-fructose cyclizes in our example reaction at the beginning of this particular video. In the case of sucrose, we can recognize as the D configuration because here at this position, we notice that the CH2OH group is oriented upward, making it the D configuration. Lactose, as we look at the structure, is composed of 2 hexoses because we have 6 atom rings here. And in the case of lactose, the building block of lactose, if we compare this to our structures of different monosaccharides, we would find that this is constructed from 1 D-glucose unit and 1 D-galactose unit. And of these 2 units shown here, the one that we see on our left is the D-galactose. I'll spell this out one time, but from here on I'll call it D-gal. And the structure on the right of this particular drawing is our D-glucose. Finally, we have maltose, which we refer to as malt sugar. Generally has a very sweet taste that's appealing for malts and other sweet treats. And maltose is composed of 2 glucose units. So the unit here on the left is a D-glucose. The unit here on the right is also a D-glucose. So we can see that glucose is a very common building block for common disaccharides that are consumed. And hence, when these are metabolized and broken down, D-glucose is the product that results from the reaction in most of these cases, because D-glucose is at least one of the 2 units of all 3 of these common sugars: table sugar, lactose, also known as milk sugar, and maltose, commonly known as malt sugar. So a key question that we need to address is, how does the so-called glycosidic bond form? The glycosidic bond is that oxygen that links the 2 monosaccharides together to form the disaccharide. This glycosidic linkage will join the hemiacetal group, typically, of one of the 2 sugar units, such as the hemiacetal group here of our D-glucose reactant, with a hydroxy group somewhere on the other reactant. In the case of this particular reaction, the alcohol group that will be linked is here, as we have placed into the box, and which I am going to highlight here in green. So in these reactions, as a general rule, we're taking the hemiacetal group from one of the two structures as a reactant, reacting with an alcohol from the other structure, and that alcohol can be at a variety of different positions of the other reactant to give different constitutional isomer products as a result of using different hydroxy groups from the other reactant. So one way that we will classify the products of these reactions, where we make that glycosidic link in the product, is based on exactly what position of the hemiacetal reacted with exactly what carbon number bearing the alcohol group that reacted to form the glycosidic link. In all of these reactions, we would classify them as dehydration because water is a product of the reaction. If the reaction is reversed, going in the other direction, water is a reactant, and that's why we show water as the arrow goes in the reverse reaction to break down the disaccharide yield monosaccharide products during catabolism. We see that water is going into the reaction rather than coming out of the reaction as a product. So when we form these glycosidic bonds by taking the hemiacetal group of one reactant with the alcohol group of the other, what is going to occur is our dehydration reaction that takes the OH group from the hemiacetal and reacts it with the alcohol group of our other reactant. Ultimately, as a result of that, forming a bond between the oxygen and the carbon atom of our other reactant. And by forming a bond between the oxygen atom of one reactant with the carbon of the other, we no longer need or have in place the OH group or the H, meaning that water, H2O, is lost in the net chemical equation for this process. So we take our oxygen atom here, and that's going to link over to the carbon atom that was bonded to the hydroxy group that's lost during the course of the reaction. So in so doing, we come down here and we form our glycosidic link by, out of this reaction mixture, losing an OH and an H to make water, and the oxygen atom is retained here to make that glycosidic link, which is really an ether link that connects the two pieces together. In order to describe that glycosidic linkage, what we do is we count the atoms, using our numbering system that we learned previously, of each of these two structures, and we describe the glycosidic linkage as a pair of numbers based on the numerical location of each of the reactants. So if it was a 1-2 glycosidic linkage, that would mean that from the hemiacetal was at position number 1, and then we linked to position number 2 of the carbon ring of our second reactant. So let's go ahead and take a look at, in this case, what would we describe this glycosidic linkage as in numerical terms. So in numbering the glucose reactant, remember that the hemiacetal group is position 1 of our ring in our aldohexose. And so that would form one of the two numbers to describe our glycosidic linkage. We would describe our glycosidic linkage as a 1, and then I'm going to draw an arrow to indicate the second position of that glycosidic linkage, and I'm going to put this all in parentheses here. And then to determine the position of the glycosidic linkage in the second reactant, our D-fructose in this case, we remember how we go about numbering our D-fructose. We looked at that at the beginning of this video. We started at position 1 was here. This was a ketose, and position 2 was where the hemiacetal was, position 3, position 4, position 5, and position 6. And if you didn't remember the numbering of this, what you would need to do is look back at the open chain monosaccharide, number that, and relate that, as we did at the beginning of this video, to how these numbers relate to one another to come up with our numbering system here. So at position 2 is where we have our originated carbonyl group that has become the hemiacetal of our starting material here. And we see in our product, as we relate the reactant to the product, that the position here that has joined up would be position number 2 of our fructose. And so we would call this a glycosidic 1,2 linkage because we start at the hemiacetal of our glucose at carbon number 1 to be specific, and the destination of the glycosidic linkage is at carbon number 2 hydroxy group of our fructose. And so that's one way that we can classify glycosidic bonds. We would describe this as a 1,2 glycosidic link. If we wanted to be more specific here, we could call it a 1,2 glycosidic link, or alternatively a 1,2 glycosidic link would be an accurate way to describe this as well. So we're showing where the glycosidic bond originates, in other words, what was the starting hemiacetal that reacted, and then what carbon number was it where we joined up with the hydroxy group to give this final glycosidic bond in the product. We can continue to do this by looking at a few more example problems, because this is one of the key skills that we learn in discussing disaccharides and classifying disaccharides. What I'm going to do here to make sure that I can classify the glycosidic bonds of the disaccharides correctly is I'm going to start with the monosaccharides, and I'm going to number those appropriately. So we start at number 1 here, was the hemiacetal carbon of this aldohexose. So we start here at position 1, as we learned to number glucose in the past and compounds related to glucose, numbering all the way through to 6. Similarly, galactose, we start at number 1 here as the hemiacetal group, and we go around the ring, position 2, 3, 4, 5, and 6. And then for fructose, here at the hemiacetal carbon, the hemiacetal carbon is the one right here, the one that's part of a hydroxy group and part of an ether group. That was position number 2 because we have another carbon that's out here. And so that carbon has to be position 1, 2, 3, 4, 5, and 6. And the reason the numbering ends up a little different here is because this was a ketose in the acyclic form versus glucose and galactose were aldoses. So therefore, the starting carbon was at the very end at the hemiacetal group, whereas in the ketose, the hemiacetal is here not at the very end, but instead at position number 2 of the ring. So going ahead and looking at how these have joined together to form the disaccharides, sucrose was composed of linkage of a fructose molecule. And by the way, we could call all of these D configuration because they all have the CH2OH group up here in the top position. We've omitted that information for now. And in sucrose, it was fructose mixed with glucose. And we would describe the linkage here between these two carbon atoms that's bridged with an oxygen here, taking a look at the numerical location where the hemiacetal group was. That was right here at position number 1 of glucose. And so going from position number 1 of glucose to looking at where that was within the fructose molecule. Fructose was numbered 1, 2, 3, 4, 5, and 6. And so we describe this as a 1 to 2 linkage. And moreover, we could describe this linkage as an alpha or a beta linkage by looking at whether the hemiacetal OH group we can infer as being up or down. So in the hemiacetal form, we would have had the hydrogen, and then this oxygen would have been originally the OH group. Since that's oriented downward orientation of the hydroxy group meant that the molecule was classified as an alpha linkage. And so we would describe this then as an alpha linked sugar there with respect to our glucose. Now, at the other position, at the fructose, we had position 1, and position 2 was where we linked together with that. Position 2 of the fructose was also an anomeric carbon in the starting material, because looking back up top here at our fructose, there was our anomeric carbon here at position 2. So we can actually classify this as an alpha molecule with respect to the glucose, and then with respect to the second unit, the fructose, we would describe this as being an alpha linkage as well. So I'm going to put this in as alpha alpha. The reason why we say it was alpha with regard to the second position is because that OH group was oriented downward here as well in the second position as we go around. Now let's continue this exercise for lactose. In the case of lactose, we have a galactose unit here on the left, and I'll abbreviate that as gal, and we have a glucose unit here on the right, matching this up with the structure here and the structure here. In the case of this lactose molecule that we have drawn, we take a look at our galactose molecule. Our galactose molecule has the hemiacetyl carbon here, or that was the origin of this, was the hemiacetyl. This is actually now technically called an acetyl group because it has an ether group here and an ether group here. So in the product, rather than it being a hemiacetyl, it's actually just an acetyl carbon because it has two ether groups directly bonded to that same carbon atom, and that's referred to as an acetyl group. And at that acetyl group, which was originally a hemiacetyl position, that would have been at position number 1, so numbering around 1, 2, 3, 4. We would call this bond that links galactose and glucose a 1 bond there, linking to, then when we look at glucose and we number glucose, the hemiacetyl group was here at position number 1, going around the chain to 2, 3, 4, 5, and 6. And that connection to the other sugar is at position number 4, was the hydroxy group of glucose that reacted. And so we call this a 1,4 connection, where position 1 refers to where the hemiacetyl group was, and now it's an acetyl group in the product. Position 4 refers to where the alcohol group was that reacted to form that glycosidic bond. So we'd call this a 1,4 linkage. There are other constitutional isomers that join galactose and glucose together that work at other hydroxy groups within the glucose molecule. So if it were a 1,3 linkage, we would have position number 1 of the hemiacetyl linking to position 3 of the glucose. And that would be a different molecule. That would no longer be lactose. It would be a different constitutional isomer and hence a different name entirely. So this is a 1,4 linkage. And then the other way that we can describe this, in addition to calling it a 1,4 linkage, is we can describe it as alpha or beta with respect to each hemiacetyl group that has joined together here. And in this case, looking at what was originally the hemiacetyl that became the acetyl, we would infer that the OH group was oriented upwards, and it's oriented upward here, and therefore we would describe the configuration of this as being a beta linkage. So we would call this a beta 1,4 linkage between galactose as the starting point where the hemiacetyl was, and glucose, which was where the hydroxy group reacted. So we'd call this just a beta 1,4 glycosidic bond. And we don't refer to the configuration of the other location here because this is an alcohol group reacting at position 4. It's not reacting at the anomeric carbon in this case, and so their alpha-beta designation is not relevant here when describing the glycosidic linkage. We used the alpha-alpha term over here when joining glucose and fructose because in that case we were reacting the anomeric carbons of each of those two molecules, and hence we needed to refer to it as alpha-alpha because the anomeric carbon configuration was alpha in both cases. Here, the anomeric carbon is only reacting from the side of the galactose, and so we just say that it's beta, and we don't need to specify the configuration of the anomeric carbon in the glucose since it's not involved in the glycosidic linkage. So with that, we'll go on to the next topic, which is that we can build up the glycosidic linkages to make the disaccharides, such as maltose, lactose, and sucrose. In the body during catabolism, the decomposition of complex molecules to release more simplistic ones and ultimately generate energy within the cell, enzymes catalyze the breakage of these glycosidic bonds. In the case of maltose is decomposed into 2 glucose units using an enzyme called maltase. And the ASE suffix here denotes for us that this is an enzyme. OSE, on the other hand, denoted that the molecule was a sugar. So keep in mind the details are important here. ASE refers to an enzyme. OSE refers to a sugar. So maltase is the enzyme that breaks down maltose, and it decomposes it into 2 glucose units. Similarly, lactase is the enzyme that breaks down lactose. So lactose, in the presence of functional lactase, is broken down into its 2 building blocks, which the 2 building blocks of lactose, were galactose and glucose. So galactose and glucose are released by action of lactase. And for people who are lactose intolerant, generally it is because the enzyme lactase is either not produced at all by their body, or a defective form, a mutant form of lactase is produced by the body. Hence, rather than lactose being metabolized correctly, instead lactose accumulates within the colon, and the gut microflora act upon lactose, and that generally generates gas, cramping, and a variety of other not so pleasant side effects. People can also be deficient in maltase as well, leading to negative side effects, but deficiency in lactase is a more common metabolic disorder that people have. So common, in fact, that Lactaid is an over-the-counter medicine that is essentially industrially produced lactase, so that a person can take that Lactaid and metabolize lactose as a result, because it provides the enzyme needed in order for them to do that. Finally, sucrose, table sugar, is broken down by an enzyme based on this trend, no surprise, called sucrase. So sucrase is the enzyme that breaks down sucrose into a fructose unit and into a glucose unit to give the product of those reactions. So